Okay, so we will start first with your question about equivalent systems. The idea of equivalent systems is that you can replace several forces and several moments, okay, by one force, one moment, or in some cases, one force. The idea is the following. So it is just here. Okay. For example, okay, if you consider the following body, and this body is subjected to several forces at different points, okay? You want to try to reduce the system of forces and moments to only at one point, okay? What is the idea here? To understand the equivalent systems, first, you say the total force F resultant can be obtained by summing all forces acting on the system, okay? So when you do sum of forces, you can find the resultant force acting on the system. But if you want to move all of these forces to one point, can you do it without adding anything? To understand why you cannot. If you have a force here, okay, and this is point O, okay, the force was acting at a certain point called A, okay? If you move in this figure, this force is doing a moment about O, yes or no?
Yes.
Okay. You multiply the force by the perpendicular distance d, okay? And according to the right-hand rule, it's, let's say, clockwise, a clockwise couple. If you want to say, I don't want to put F at A, I want to displace F to O, and you want now to put F at point O. If you put it as it is, without adding anything else, what is the moment of F about now in this new figure?
0.
0. So you can you say that the two systems are producing the same effect?
No.
No. For this reason, okay, for this reason we say when we displace a force from one point to the other, in order to have equivalent system, okay, we should have the same moment about the new point. And if you displace F to O, you still should have moment about O. According to this figure, what is the moment about O? F times D, okay? When you put F at O, it cannot itself produce any moment about O. So you can say, I displace the force to O, but I add at O a couple moment, M, equal to the moment of F. So I should add a couple equal to the moment of F about O. So here you should add a clockwise moment equal to F times D. Okay. This is the idea. Did you got it here in this simple example?
Yes.
Now, what if you have 3D? If you don't have 2D case, if you have 3D case, each force that you displace to a certain point, you should add its moment about the point. This is why they say, for example, in this figure, if you have F1, F2, and F3, okay? And you want to displace all of these forces to O, you should do first, what is the moment of F1 about O? It's R1 vectorial F1. The moment of F2 about O is R2 vectorial F2. And if you have a third force here, for example, F3, you should do R3 vectorial F3. This is, okay, this term. This is this term, sum of moment. So this term represents moment of all forces acting on the rigid body about O. Now, sometimes, in addition to forces, I can give you couple moment acting on the body. And if instead of putting a force, I represent in 2D, I represent a couple by an arrow like this, okay? In 3D, I replace a moment couple by a vector, okay, with an arrow like this. So it's a couple moment. We have seen together that a couple moment is independent of the point, is a free vector. So whenever you have a couple of forces, they will produce the same moment about any point in space. So when you do sum of moment about O, you take the couple moment as it is. Okay? So this is the summation of couple moments acting on the body. And this is the summation of moment of forces about the point that you want to reduce at, which is O. In this condition, you can say that I can reduce several forces and several couple moments at one point. At this point, I just represent the system by one force, one moment. Clear?
Yes, thank you.
Okay. Other question? Other question on the course material? Concerning distributed load, do you have any problem with it? If you want, I can go again through the material, but to save time and to do more problems, we can, if it's clear for you, if the whole ideas are clear for you, you can move to problems. Let me know if you want me to repeat anything here in the course material slides.
دكتور أنا بس عندي سؤال إنه إحنا
Yes.
لازم نكون نعرف كيف نحول من قلبي
No.
لكيلوغرام مثلا شيء
No,
هيك.
no, you don't have to convert. You can, if you have English units, keep them English units. Just you should know that in English units, G is not 9.81, it's 32.2 feet per second square. Okay? And force will be in lb, mass will be in slug. You don't have to do any conversion.
أوكي دكتور.
Okay. Other questions?
I have a question.
Yes.
To calculate the moment of a couple,
Yes.
we always take the perpendicular distance between them or any distance.
Okay, look, it depends on the method you are using. Yani if you have two forces, okay, and you know the plane, and for example, if you have two forces in xy, okay, you are sure that the moment will be in which direction if the two forces are in plane xy? The moment vector is always perpendicular to the plane of forces, okay?
About that.
Exactly. So if you
Yeah.
if you know the plane of the forces, no need to work with cross product or vectorial product. You just say one method is the following. I find the perpendicular distance between the two forces. And here I cannot take any distance in this method. I take the perpendicular to say that the magnitude is F times D. Okay, so for the magnitude, you cannot take any distance between 2 points. You take the perpendicular distance between the forces. And then to find the direction, you do the right-hand rule. If you do the right-hand rule with your hand, you will find that your thumb will point here downward. So your vector moment is along minus z. Okay, this is a first method. But you can also use vectorial or cross product. If you want to use cross product here, you can take any vector. Yani if you have any point on this line, any point A, okay? And you know any other point on the opposite force B. You can take vector AB, vectorial, this force F, okay? Here you don't have to take the perpendicular distance. You take the vector joining one point of the first force on any point on its line to any point on the other force. So pay attention, there is a difference between the two. If you want to use cross product, you can take any 2 points, any vector position. But if you want to get the magnitude using F times D, D should be the perpendicular between the two forces. And we do it only in case the direction of the moment is really simple, like here, for example. But if you have an inclined plane, let's say, You cannot know what is the direction of the moment vector. It's easier for you to work in cross product or vectorial product.
Okay.
Okay.
Thank you.
Welcome. Other questions on this?
Doctor,
Yes,
please can we do the distributed?
of course. We can do the distributed. Okay. First, what is a distributed load? A distributed load is a load that is acting in a continuous way over a surface. It's not at just one point, okay? So if you have a force just acting at one point, we call it concentrated force. If you have, for example, if you have a beam, okay, and you have a man standing on it, you should consider the weight of the man. The weight of the man is applied at a single point of your beam. This is a concentrated force, while a distributed load is like, for example, the action of wind. It's the result of a pressure. The pressure is acting over a surface, not only at a certain point. It's in a Newton. If we talk about an area, we say pressure is a Newton per meter square. If we talk here about a line, we have a force per unit length. So the distributed load is in kilonewton per meter. Okay? Now, how to find the total action? The idea is if I have a distributed load, and again, I go back to the concept of reduction. I want to reduce it to a single force, okay? And single moment at a certain point. So I say, how can I find an equivalent system consisting only of a concentrated force and a couple? First, plus we'll see together here that when a force and a couple are perpendicular, you can move the force in a way to produce the same couple. Then you don't need to represent your system by a force and a couple. You can reduce your system to one single force. So keep in mind, we have particular cases where we can reduce the system to one single force, okay? This is the case when you have the force and the moment perpendicular to each other. To understand better what I am talking about, I'll give a simple example, okay? Consider the following beam, and you have on it a distributed load that is constant. It's in rectangular form, okay? So for example, I have 10 kilonewton per meter, let's say, okay? And I know that the length of my beam is 2 meters. So it's very simple. How to calculate the total force? I multiply 10 by 2, okay? Because I know the length and I know the load, so I just have to multiply 10 times 2 equals to 20. Okay, so this is 20 kilonewton. But I should ask myself, where should I put this force? Okay, and if I want to reduce my system to a single force, where should I put this force? Here, why it's simple? Because I have a symmetrical case. If I have a symmetrical case, then the force should be just at the middle. Okay, so my force is just at the middle of the beam. And I can say I can replace this force by one force acting at the middle, equal to 20 kilonewton. And if the distance is 2 meters, then it should be at 1 meter from the origin. Okay, so now I can say the following. If I have a general case, I don't have this very simple scenario. How can I reduce my system to a single force? I should think in the following way. First, as a first step, I can reduce my load to 1 point. Okay, so I can reduce my system at O. Okay, guys, please just give me 1 minute, please, okay? Okay, so we were saying here that we need to reduce at a point, okay? So first, we should ask ourselves, the first step to reduce a system to 1 point is, as we said before, to find the resultant force, F resultant, okay? When you have a distributed load, to calculate the resultant force, you have the following. You have a function that can be variable, okay? So you know that from mathematics, whenever you have variable function, okay, you need to find the total force. You can divide it into small forces. And if you have this, let me change the color, okay? You have at each point, you have a new value of W. So I can divide this load into small forces, very small forces, okay? And so I just have small rectangles, and to get the total force, I need to add all of these small forces. So each small force will act on a very small element. I will call this, the thickness here, dx. So if this is dx, okay, a small force df acting on the beam will be equal to omega times dx. Okay, and now I want the total force. How to get the total force? In mathematics, you say I should integrate. You need to get the, if you want, the force is equivalent to what here? When you do omega times dx, it's equal to this area, to the area of this rectangle. Okay, so to get the total force, it's like to calculate the total area under the curve. And you know, mathematically, the total area under the curve is calculated by integration. So you can say that F resultant is equal to integral dF equals to integral W dx. So from here, you can deduce that if you have any load acting on a line, to reduce it to a single force, all you have to do is to calculate the area under the curve, okay? And we'll give you simple cases. So you are not responsible, if you want, of complex cases where the load is varying with any arbitrary function. We'll give you or rectangular loads like this rectangle, or triangular load. So all you have to do is to compute the area. If you have a triangular distribution, for example, okay, you just have to do length times W over 2 to get the area under the curve. So whenever you have a distributed load, the first step to do is to calculate the area under the load to find the resultant force. This is step 1. But now, when you find the resultant force and you put it at O, you cannot put it at O without adding anything. You need to add the moment it's producing about O. And to calculate the moment it's producing about O, you say each force, each elementary force here is at distance x from O, okay? So for each small force, what is the moment? For each small force, the moment dm is df, which is the elementary force, times the distance x, which is the distance from the force to O. And we have seen together that df can be replaced by omega dx. So it's equal to integral sorry, before doing integration, it's equal to x omega dx. Okay. And now to find the total moment, what do we do? The total moment is integral dm, which is integral x omega dx. Okay. Now, omega dx represents the area dA. And you have a mathematical formulation stating that integral x dA, okay, is simply equal to x bar, which is the position of the centroid of the area times the area. What is the area? We said the total area is the resultant force F resultant. Okay, so what do we understand from this formula? We can say always the resultant force, okay, can be placed at a distance from O equal to x bar, which is the centroid of the area. And here, by symmetry for a rectangle, we directly said it should pass by the center. Why it should pass by the center? Because the centroid of the rectangle is at the middle. So if you want to reduce to a single force, this single force should pass by the middle of rectangle. But if you have a triangle, mathematically for a triangle, the centroid is at, if this length is L, okay, if this length is L, you have the centroid is at 2/3 L from the point O. So this is 2L over 3. Okay, and this is from the other extremity, it's L over 3 from the base. You have L over 3. Okay, so we can say whenever we have a distributed load, if we want to replace it by one single force, the resultant should be equal to the area of the load, and the point of application should pass by the centroid of the area. Okay, and then if you want to take the force to O, if you want to replace it at O, you need to say, I need to consider the couple moment x bar times FR at O. Okay, so I will repeat. Here, for example, let me take this example to illustrate what we mean. Okay, you have here one triangular load, one rectangular load. The rectangular load, you can replace it by a force first equal to the area of the rectangle. What is the area of the rectangle here? You have 40 here times this distance, which is 4. So 40 times 4. Okay, so you have here 160. This is your force, but what is the point of application of this force? It should pass by the centroid of the rectangle. So it's just at the middle. Okay, so I can replace this rectangle by one force passing by the centroid of the rectangle. The magnitude is 160 and it's just at middle of rectangle. So if this distance is 4, from this point to this point, I will have 2. And if I want the distance from the origin O here, I have here also the distance is 4. Okay, so the total distance of F1, let us call it. So this is F rectangle F1. The distance of F1 from O is 6. Okay, now what about the triangle? For the triangular load, also I can replace this force by one force, and the magnitude of this force is equal to the area of the triangle. The area of the triangle is the base 40 times 4 over 2. 40 times 4 over 2 is 80. So the magnitude of the force is 80. Now, what about the point of application? Also, it should pass by the centroid of the triangle. We said that the centroid of the triangle is at 2/3 from this point and 1/3 from the base. Okay, so if I want the distance from O, I should move a distance of 2 times 4 over 3. 2 times 4 over 3. 2/3 of 4. Okay? So now I say I can replace this triangular load by 1 force F2. So what I did until now, I reduced the distributed load to concentrated forces. What is the next step? They asked me to reduce to one single force. I want to reduce the whole system to one single force, okay? To do this, the method is always the same. I say, let me first reduce the system at any point on my figure. And here O is the easier point. So let me reduce first the system at O. What do we mean by reducing the system at O? So I want to move all forces to O. But when I move a force to O, I should add the moment it's producing about O. Okay? Yani now, what you want to do is the following. You want to put F1 at O. But if you displace F1 from its position to O, what should you add? You should add the moment of F1 about O. How to get this moment? Look, we said that F1 is at a distance of 6 feet from O. So if I want to move F1 from this position to O, what should I add? I should add the moment it's creating about O. This moment first is clockwise. So I put a clockwise moment like this. And I say that moment about O, I will call it MO1, which is the moment about O of F1, is equal to F1, which is 160, times the distance, which is 6. Okay? So first I moved F1 to O. Next step, I will move F2 to O. If I move F2 to O, also I put F2 here. So what is the total force now acting at O? It's F1 plus F2. So this is the resultant. I add the forces. Okay? Now, when I displace F2 from this point to O, as we said, we should add the moment of F2 about O. So I should add moment MO2. Okay, MO2, which is equal to the value of F2 is 80 times the distance to O2, which is 8 over 3. So I multiply by 8 over 3. Okay, and now what is the total couple? Since both are clockwise, I can say that the resultant moment, M resultant about O, is the summation of the two. It will be in the clockwise direction, okay? And it will be equal to MO1 plus MO2. So what I was able to do until now is to reduce my distributed load at one point. So if I want to present my system, I can just say this is my wall, okay? This is point O. At O, I have F resultant, which is the summation of the two forces, okay? And I have M resultant, which is MO1 plus MO2 in clockwise direction. But the question was not to reduce at O. The question was to reduce to one single force. And why here is it possible to reduce to one single force? Because look, if I say I want to displace FR in a way to produce itself this moment about O. Okay, so here I want to change the location of F and find what is the location. I will call it Y. What is the distance Y I should put my force at in order to produce equivalent moment about O? So my purpose is to reduce the system to one single force. I want to replace the force and the couple by one force only. Okay? Of course, the magnitude will remain the same. And to determine what is the distance that I should place the force at, I say, what is the condition for equivalent systems? Equivalent systems should have same resultant force and should produce same moment about any point in space. So in this figure, if I want to present as a system by just the blue force, what is the moment it's creating about O? It's Fr times Y, okay? And I want that this moment should be equal to the moment of the resultant about O. Because when the force was at O, when Fr is at O, it cannot produce a moment about it. So what is the moment about O? It's just M resultant about O. Okay, so if I take the green system has a moment about O equal to MRO, while the blue system has a moment about O equal to FR times Y, because I want to find the location Y in a way to just have a single force without any couple. Okay, so for the blue system, the moment about O is FR times Y. For the green system, the moment about O is MRO. Okay, so I can say then that what is Y? I can deduce what is the location Y I should put my force at to have a single force. It's MRO over FR. Okay, clear? Any question on this? Okay, now I want to tell you, if I select any other distance different than Y, okay, if I tell you, for example, now deduce the reduction at this point here, and this point is at a distance D. So let us change the color. I need to have a new equivalent system, okay? I need to have a new equivalent system. And this equivalent system should be at a distance D from O, different than Y. Since D is different than Y, okay, of course, when I reduce at this distance, I need a couple. Can you tell me here, according to the figure, do you think that the couple will be clockwise or counterclockwise? So if I call this point A, okay, can you tell me why M at A should be counter? Yes?
Why do we need a couple?
Okay. Why do we need a couple? Because the only location, okay, for which you don't need a couple is at distance Y. Because when you put the force at a distance Y, okay, you found Y in a way that the moment of FR about O, which is FR times Y, is equal to MRO. And what is the condition to have equivalent systems? They should produce the same moment about any point in space. Okay? So if you take point O, look at the green system. For the system drawn in green, what is the moment about O? The force FR is passing by O. Can it produce any moment about O?
No.
No. So you just have the couple. Okay? So when you calculate moment about O, it's equal to the couple MRO. Then we said that what if we want to displace the force in a way to produce itself this moment about O? Yani we don't need then any additional couple to have equivalent system. Yani I want to find, if I ask you what is the position for FR to just reduce the system to a single force, you tell me I should move it in a distance Y in a way to create about O which moment? What should be the moment about O to have equivalent system? It should be MRO, okay? So if you want, there is a single location, which is Y distance, in a way that when I put the force at this point, to have equivalent systems, I don't need to add any couple. While if I move it to a distance smaller than Y, okay, the moment it will create about O will be smaller than MRO. So I need an additional couple clockwise to help it to have a moment about O equal to MRO. And if I exceed Y, the moment of the force itself about the point O will become larger than MRO. So to go back to MRO, I will need a couple in the counterclockwise direction. If you want, I will give you an example with numbers to understand better. Okay? Yeah, I will open a new meeting to give you an example with numbers to understand what I mean in a better way. Okay? Yeah, I will open a new meeting.
Okay.